So welcome to another session of ME324, and in this section we will be looking at about structural dynamics. So all this time we were discussing on static problems, especially which belongs to structural as well as non-structural static problems. In the previous session we discussed about heat transfer applications, steady state heat transfer applications. So now we will be moving into the dynamics. Let's say we will be focusing on elementary problems, including time dependent nature. We will be looking at time dependent problems. So when we talk about time dependent problems, we will first I will try to introduce the basic concepts using a single degree of freedom spring mass system, which is the fundamental system for understanding a dynamic, how the dynamics can be incorporated into a finite element for a simulation formulation. And of course, we will be discussing about stress analysis of one-dimensional bar and a beam. And for this, we will be using the basic necessary equations for structural dynamic analysis and try to develop them both using lumped and the consistent mass matrices. Some of the techniques which we use to analyze bars and beams, trusses and frames, and so on and so forth. So again, the method, the steps that we follow is quite similar to what we have done previously, but there are certain changes now. The only change is that apart from the static loading, we also have to consider the dynamic loading which is applied on the system. So which is caused due to acceleration, and we will be considering the inertia or the mass of the system. So things like that, we will be slightly using these concepts to modify the existing equations and let's try to solve a time dependent problem. And when we talk about time dependent problems, so yeah, when we talk about dynamics of the system, or when we consider a structural problem, and when we try to incorporate the dynamics or time dependent nature into this problem, the most fundamental arrangement that we would like to consider to understand the concepts is to model the system using or analyze the system using a spring mass system. So we are trying to analyze the dynamics of a spring mass system. So for this, we will consider a motion of a single degree of freedom spring mass system, just to get familiarized with the basic concepts, and we will later onwards apply them to such as bars and beams, more structural components. So if we consider a simple spring mass system which is subjected to, let's say, a time dependent force, and assume that we have a mass which is coupled to a spring having a spring constant K, and the mass of the block is M, and this block is subjected to a time dependent force, let's call it capital FT, and the coordinate, which is, since we analyze a single degree of freedom, we assume that the force time dependent force is applied in the x direction, and it is fixed on the left hand side and it is free to move on the right hand side. So here the spring force, if we analyze the, let's say, the free body diagram of the mass that we are interested in this case, there are two types of forces: the time dependent force, which is applied, and of course the opposing force, the force applied by the spring, let's call it capital T, and the T is equal to K times X, the spring constant times the displacement. And since we know when it is subjected to an unbalanced force, the mass is subjected to acceleration. What we can do is we can simply apply the Newton's second law of motion. Which is nothing but the force is equal to the mass times the acceleration, of course, due to the unbalancing force. And then we obtain the equation of motion in the x direction. When we apply the Newton's second law, the force applied, that is Ft, minus the force generated by the spring, of course it's a simple K, is equal to the mass times the acceleration term. So here the dot over the variable, of course, denotes the differentiation with respect to time. That is, of course, known to you. So dot stands for, of course, whatever a function which is differentiated with time. So if it's double dot, you differentiate it with 2 times. Yeah, with differentiate a variable with respect to time 2 times. So in the standard form, if we arrange the equation in the standard form, what we obtain is, of course, there's a term, acceleration term, mx double dot, kx, and the time-dependent force applied on the system. So it is clear that this equation is a linear differential equation, and we can see it is a second order. And of course, for this type of equation, the solution for displacement x, which basically consists of homogeneous solution and a particular solution, 2 solutions. Those standard analytical solutions for this force type of vibrations are commonly found in vibration books as well as dynamics, the books relating to dynamics. So here I will not really represent the analytical solution of this equation, because the intention of this section is quite different. However, we'll try to solve this equation by using approximate, let's say, numerical techniques, of course. And let's try to also consider an homogeneous solution of this equation, which can be obtained when the right-hand side of this equation is equal to 0, when the force applied to this equation is 0. So we can say we can analyze this equation, a number of, let's say, useful concepts regarding, let's say, vibrations can be obtained by making the right-hand side of this equation is 0. That is, in other words, by considering a free vibration of the mass. So when Ft, the force time-dependent varying force, is 0, what we can define in this case is an omega term, which is equal to K divided by M. So by setting the right-hand side equal to 0, we can simply write, so instead of K, we can write omega squared M. So by setting the right hand side 0 and dividing by M, we can rearrange this equation into this format. right. So here, the omega, this is, I think maybe this is already familiar to this type of equation, a second order differential equation, where omega term is called the natural frequency or the free vibration of the mass. Yeah. So omega is the natural frequency of the free vibration mass. Yeah, this usually expressed in terms of radians per second or revolutions per minute, if you may. So you can see that from this equation 10.1.3, the natural frequency of, let's say, this structural element depends on the spring constant or the spring stiffness K, and of course the mass of the body. So the motion defined by this equation, that is 10.1.4, this particular equation here, is called a simple harmonic motion. And of course, we can identify the amplitude of the vibration here, and of course the we can identify the amplitude of this vibration, and of course we can define a time interval which is required for the mass, the block of mass, to complete one full cycle of motion, which is called the period of the vibration. We can define it by tau, which is equal to 2 phi divided by omega, where tau stands for the period of vibration. Okay. So I think these are the important concepts that we require for analyzing time-dependent, let's say, structural problems. And of course, it is also important to note that all vibrations are damped to some degree by friction forces. Yeah. So depending on the application, these forces may be caused due to dry or Coulomb friction between rigid bodies, and of course by internal friction between molecules, if it is a deformable body, or by fluid friction, if we consider a fluid problem, where a body moves in a fluid. So the damping results in the natural circular frequencies that are smaller than that of undamped system. So the maximum displacements are also smaller than when compared to damping when damping occurs. Yeah? Whenever there's damping, the maximum displacements are also smaller in such instances. So keeping this aside, I mean, since we already have some background information, we can focus on, let's say, the derivation of the bar element equations. Yeah, call it 10.2. Direct derivation of the bar element equations. All right. So we will now derive the Feynman element equations. So for a time dependent, let's say dynamic stress analysis of one-dimensional bar, we have already done this previously for static stress analysis system. And it should be noted that the steps that we use for deriving the dynamics equations, or steps that we will be using for deriving the dynamic equations, are the same as those used for deriving the static equation. So only minor changes will be required, and I will highlight you whenever these minor changes appear. So our first step, as always, is to select the element type. And in this case, we use a typical bar element. Let's select a bar element having a length of L and a cross-sectional area A. And let's assume the bar has a mass density of rho. And the nodes 1 and 2 of this bar is subjected to an external time-dependent loads. Let's name them here. So the forces are applied in x direction. So we go back to our local coordinate system, d1 x hat and d2 x hat are the displacements in the local coordinate system corresponding to node 1 and 2. Node 1 and 2 is subjected to local time-dependent forces in the x direction. Let's call it F2 x hat and t because it's time dependent. Similarly, F1 x hat, and let's use a t to include the time dependent nature of the problem. So the external loads are referred by this term where we mentioned, of course, the local element forces, the time-dependent elemental forces. So the next step is to select a displacement function. Again, we assume a linear displacement function in the x axis of the bar. So the typical step, the displacement function can be described using a linear equation. And if we use the shape functions to describe this displacement function, of course, we can rewrite it as u hat is equal to, now n1 is the shape function corresponding to node 1, and n2 shape function, node 2, okay. So we know that the two shape functions with the help of, let's say, if derived for this particular element can be written in the following way: n1 is equal to x hat divided by L. So we know when L is when x hat is 0, then n1 is 1, of course, so which is right. N2 is nothing but x hat divided by L. So at a length of L, the N2 shape function is equal to 1. So this is correct. Both these equations are correct. Because at the particular node, the shape function, the value of the shape function should be equal to 1. So we can write this, we can use this equation now further again, and also think about the next step, that is to define the stress strain displacement and stress strain relationships. Yeah, so I will not write down because we have already gone through these steps umpteen number of times. So I will simply write down the the strain displacement relationship, the displacement relationship, which is given by the displacement function partially differentiated with the variable. So we know we can write it using the B matrix and the D matrix, D hat matrix, where B matrix is equal to -1/L, and the D hat matrix or column matrix is equal to D1x hat and D2x hat. All right. So we know the stresses are related to the strains via the constitutive matrix, D matrix, which includes the material properties. Yeah. So in other words, it is D times, we know the strain matrix, epsilon x is equal to B times D column matrix. Okay. So we are now, we have found the relationship between the stress and strain. In the next step, we have to now derive the element stiffness matrix and as well as mass matrices and corresponding equations for this particular problem. So we know the bar is not in equilibrium because it is under time dependent force. So we know we can say that because it is not in equilibrium, F1x is not equal to F2x. And therefore, we can again apply the Newton's law of motion, which is nothing but the force is equal to the mass times acceleration. So let's apply for this for each node, because each node is under and experience some movement and it is not under equilibrium. So when we consider or when we try to apply this Newton's second law for each node in general, we can write this equation for each node as the external applied force, that is the externally applied force minus the internal force, yeah, is equal to the nodal mass times the acceleration. So when we are finding kind of like an equivalent term, we can use this formation. So by adding internal force to the MA term, we have, so in this concept, we can write, yeah, the force, yeah, we can say the force applied, the time-dependent force corresponding to time-dependent elemental force corresponding to node 1 is equal to whatever the internal force plus the acceleration terms or the forces corresponding to, let's say, the accelerations. That is, m is the mass and we have to be multiplied by the acceleration. What is the acceleration at node 1? Node 1 acceleration at node 1 is d1x hat when you differentiate it 2 times with respect to t. Similarly, we can write the external force applied at node 2 to be equal to whatever the internal force, contributions from the internal force, the mass at node 2, and the corresponding acceleration at node 2. All right, here the masses M1 and M2 are generally obtained by lumping them, lumping the total mass of the bar equally at the two nodes. Yeah, so we lump the mass. So we call it the lumped mass matrix, or lump mass method. So how do we lump it? We lump it such a way that the total mass of the bar is equally distributed at the two nodes. So we do it in such a way that M1 is equal to the volume A times L gives E divided by 2. Similarly, M2 is equal to rho AL divided by 2. That is how we lump the mass to the two separate nodes. So we can now replace the internal forces applied in these cases, these internal forces, using the spring constant K and the displacement D from the previously defined equations. Yeah. So in general, we can write, let's write it before we write, let's say that we can write the force matrices, these two force matrices in the form of the force, these equations given by 10.2.7, let's put them in the matrix form. So on the left hand side, we have the time dependent forces acting on node 1 and node 2, time dependent elemental forces. And of course, then we have the internal forces, internal force contributions at node 1 and node 2. Then we have contributions from the acceleration terms. We know that these have to be multiplied by the accelerations at node number 1 and accelerations at node number 2. We have to multiply with the mass matrix. So now we can replace this set of equations using the spring constant, let's say K times D representation. So we know the internal forces due to static loading, so to say, due to the internal forces. We can write it in this using the spring constant and the displacement to obtain the elemental equations in the following. Say whatever the time dependent force matrix can be written using the stiffness matrix D. This part corresponds to the internal forces, and then we have the mass matrix and of course the acceleration matrix. So here we know the spring stiffness matrix for a bar is equal to AE divided by L, cross-sectional area modulus of elasticity divided by L, and we have it, if it is a single degree, of course, we have this equation, if you can recollect from all the previous lessons that we learned. And for this bar element, the stiffness matrix or the mass matrix, we can write it as, we know rho is the mass density, A times L gives the volume, so the total mass into 2, which is equally distributed among the two nodes. This is called the lumped mass matrix. also we can write the acceleration terms. So yes, you write it as 10, 10, 12. Right. So one interesting observation is that the lump mass matrix only has diagonal terms. Um, yes.